So I'm going to be talking today about a linkage property in graphs that we're going to call forordered, and we're going to define that right away. So a graph G is forordered if for every set of 4 vertices in the graph, there's a cycle through the vertices in order. And just to show another example of that, of course, you can generalize this to k-ordered graphs. And then a graph G is k-ordered if for every set of k distinct vertices in the graph, it has a cycle through those k vertices in order. Now, this is a general, so in particular, the question we're going to be studying today is the minimum connectivity that guarantees that a graph has this property. And so we're going to call that number f of k. So f of k is the minimum connectivity so that every f of k connected graph is k-ordered. And one reason that we're interested in this is as a generalization of this classic theorem, which says that k is the minimum connectivity, so for every set of k vertices in the graph, there's a cycle through those k vertices. So we're now saying what happens if you want the cycle to contain the vertices in order. So how does this connectivity change if you require the cycle to contain the vertices in order? And for k less than or equal to 3, there's only one cyclic ordering of k vertices on a graph. And so the reason we're interested in f of 4 is because this is the smallest case that's different from the original problem. So for k equals 4, there's 3 ways of ordering 4 vertices on a cycle. And you can see that these are all different by looking at what vertex is across from C1. And that's why there's exactly 3 too, because once you know what vertex is across from C1, there's only one way of putting 4 vertices on the cycle. And in order to talk about the prior work on determining this minimum connectivity, we're going to define just what it means for a graph to be k-linked. So a graph is k-linked if for every set of 2 k vertices in the graph, S1 through Sk and T1 through Tk, there exists a set of k paths from S1 from Si to Ti. And so the first time that linear connectivity was found was Belobis and Thomason, showing that 20k connected graphs are k-linked. And then Kawarabashi, Kostachka, and Yu were able to improve this to show that 12k connected graphs are k-linked. And then the best linear bound currently is the Thomas and Wallen proof, showing that 10k connected graphs are k-linked. And I should also say that for the case of k equals 3, there's a better bound. We in fact know that 10 connected graphs are 3-linked, but this is the best known for k equals 4. And so for k equals 4, this gives us the best known upper bound currently, which is that f of 4 is less than or equal to 40. And so what about the lower bound? Fodry showed in a survey on k-ordered graphs that f of 4 is at least 6, and Ellingham, Plummer, and Yu were able to find a 6 connected graph that is not forordered, and that means that f of 4 is at least 7. Now we're going to be, and so our theorem improves the upper bound to almost equal to the lower bound and says that in fact 8 connected graphs are forordered. And now next I'm going to be talking about these 2 counterexamples and what we might expect for a structural characterization of the ordered property. And this is also going to lead us to the main idea that we use in the proof. So that's the question that we're going to be looking at next. What do these highly connected graphs that aren't forordered look like? And I think this is what I just said. This is going to lead us to a conjecture for an actual characterization, and then the main idea for our proof. So this is the graph that Fodry uses that isn't forordered. It's a 5 connected planar graph, and in fact then it doesn't even have these 2 bold paths listed. And in fact, it turns out that the converse is true by Paul Seymour. If G is a 4-connected graph with 4 distinct vertices in the graph that doesn't contain exactly these paths, then you can draw the graph on the plane with the 4 vertices in this order on the boundary. And so now, next we're going to look at what happens for graphs that don't contain a C1, C2, C3, C4 path. Right? So this graph doesn't use everything possible because it doesn't even, not only does it not have a cycle through the 4 vertices in order, but it doesn't have the 2 bolded linked paths. And so the graph that is 6 connected that's not forordered is going to use the fact that it doesn't have a C1, C2, C3, C4 path. So This picture has a planar graph with C1, C3, C2, C4 on the boundary in that order. And then we're identifying the vertices in the C3, C2 path with the middle vertices of a 3x(n) grid. So this top part here is a 3x(n) grid where n is the number of vertices on the C3, C2 path. And then this is a planar part. And I'm going to show that this graph doesn't have this bold path here. And also just a note from Paul Wallen's talk, this is basically taking a planar graph and then adding a vortex of depth 4 across the top where you have a lot of crosses. So we've actually seen this graph already so far in the talks today. Okay, so this is actually the one proof that I want to do here in order to actually show that this graph does not have the bolded path. So suppose that it does have such a path and call that path P. And then we're going to let the vertex V be the vertex along this path closest to C1 so that V is not in the planar parts. Okay, so just let me state that again. So V is the vertex closest to C1 along this path that's not in the planar part. Now, if this vertex does not exist and all vertices in the path are in the planar part, or if V is simply not in this blue subpath, then the blue subpath separates C3 from C4, which is of course a contradiction because we know that once we remove this path, there's still a C3, C4 path. So that shows that V must in fact be in this blue part. Right, so V is in this part right here. And now we're going to let U be the vertex immediately before V. Note that U can't be this vertex because we chose V to be closest to C1 so that it was not in the planar part. And likewise, U can't be this vertex. So in fact, U is that vertex. And then look at this subpath from C1 to U. Again, by the choice of V, this subpath is totally in the planar part. But then that means that this vertex right here, right next to V, is a cut vertex once you delete this path that separates C3 from C2 and C4, which is of course a contradiction because we know that this path exists once we remove the blue path. So we've shown that this particular graph does not have a path through C1, C2, C3, C4 in that order. And this is eventually going to lead us to a structural characterization that's a generalization of the four-planar theorem. But we're going to have a few other operations that we can do on this grid. So first of all, you can take a 3x1 segment of the grid, which we're going to call a rung, and you can add a planar graph. So this graph is actually drawn in the plane, right? This gray part is a planar graph with the given vertices on the outside. Another operation you can do is you can contract the two vertices in the middle, right? So we're taking these two vertices and we're contracting them. And that gives us this hourglass shape instead of the 3x1 square. And then once you've done this contraction, it turns out there's actually not enough vertices there for you to use, basically. And you can add anything you want attached to these 5 vertices. In particular, you can make the induced graph on these 5 vertices a K5. And so there's a few other operations like that, but I don't want to get into the particulars today. Just know that each of them kind of look like this. There might be some other small cuts, and then you have other conditions like planarity. So the informal statement of this theorem is that if G is a 4-connected graph without this path, so we're calling this whole section here a ladder. That's what the ladder is right here. And so then in fact G does consist of a planar part and then a ladder attached along the C3, C2 path. And so we can think of this as one case where we can get an exact structural theorem as opposed to the general graph minors. So this is an if and only if statement. And of course I'm stating it informally, but this is an if and only if statement in terms of adding a vortex to the top of this. Okay? And now another observation to kind of get us started for the four-ordered question is that this graph has no cycle through 4 vertices in order. And I'm not going to prove that today, but again, let me just say that this is So we just take another 3 by n grid, where n is the number of vertices in this C1, C4 path, and we identify the middle vertices along this bottom boundary. Okay, now I'm going to go from this to the main proof idea that we've used. And so somehow, if you want to take this part right here, so this is a subdivision of this graph, and we're going to look at this subdivision, which is related. So you can see here that this bolded part is a cycle through C3 and C2, C3, C2 cycle. And this bolded part down here is a C1, C4 cycle. And then it turns out to be useful for us to look at this subdivision. Instead of taking this C1, C3, C2, C4 cycle, we take a disjoint cycle and then add paths from the C vertices to that cycle. And this gives us the start of the main proof idea. First, we find this subdivision where C1, C2, C3, and C4 are fixed vertices. And then let me denote H as the induced graph on the set of all vertices of G except for the vertices in this cycle and this cycle. Right, so H is G whenever you delete the vertices of this cycle and the vertices of this cycle. And so it turns out that if you choose this subdivision in a certain way, you can actually get that H is 2 connected. And this is related to work on the Lavoie path removal conjecture. We sort of take some ideas from that and expand on them in a number of ways that we can actually get the whole, this whole subdivision. So for instance, first we want that the sum of these 4 edges is minimum because, first we want that the sum of these 4 paths is minimum because we'd really like them to be edges. And then after that, we can get that H is 2 connected. Okay? And then once we have the H is 2 connected, we can use that to get the H is 4 connected. And that gives us that H is planar. And so then we have this planar part that's attached to 2 cycles. And we can use planarity to first find a small cut set in H, and then lift that, if you will, to a cut set in the entire graph. Okay, and so I want to talk a little bit about future directions. Of course, the most obvious thing we could look at next is, do there exist 7 connected graphs that are not 4-ordered? Is the answer for this f of 4 equals 7 or f of 4 equals 8? But the next and perhaps the more interesting question is, can we get a complete structural characterization of when a graph doesn't contain a cycle through 4 vertices in order? Oh, these are mislabeled. It should all be up by 1. So can we get this structural characterization? And now I'm ready for questions.
Any questions?
In your definition of k-means,
Okay.
do the starting vertices and ending vertices have to be disjoint?
Yes, in the definition that we're using. That's right.
Any other questions?
So is this a conjecture? Do you think
This is, yeah, so it's a little bit interesting because there's not symmetry here, as in the paths at the top could be C3, C2, and C1, C4, or they could be or they could be C1, C2, and C3, C4. So I think that this may actually require that there's no 5 separation, or that the graph is 5 connected. So I think you need a little bit more connectivity in order to guarantee this. But it's also...
that connectivity you think this should be?
Yes, yeah. And pretty quickly in our proof, the symmetry disappears. So the only problem with symmetry is dealt with in the first couple of pages of our proof. And so I think that with something like 5 connected, you can get this.